Alright, let's go ahead and get started. Before we start this, two quick announcements. One, yes, I did put up a key for the antibiotics that we covered, or that we started covering on Monday. So where that assignment was in the antibiotics lecture 1, or lesson 1. I've actually just included an additional file just below the one that you downloaded onto your computer to fill out that table. So it's under that homework assignment. What do I want you to know from it? The most important things to get out of it are, for the different classes of antibiotics, knowing the protein target and knowing what it inhibits. I'm not going to ask you to memorize the spectrum because, as Abby pointed out, different sources give different information on spectrum. Rather, I want you to be familiar with the terminology of broad spectrum and narrow spectrum and be able to identify times in which we might use one or the other. And that is a concept that we will begin to talk about, but we'll come back to as well, actually, in the next few weeks. Now, there are a couple of exceptions. I do not want you to know the protein target for ethambutol and isoniazid. Okay? The name dihydropteroate synthetase is long and makes no sense whatsoever. So that's one I do not care for you to know. The second one that I do not care for you to know is the protein target of the sulfa drugs. Maybe that's the dihydrofolate synthetase, sorry. Or teroate synthetase, yeah. The other one's INHA or something like that. I do want you to know the penicillin binding proteins. I do want you to know gyrase, ribosome, RNA polymerase. What am I missing? I feel like there's one other one. Oh yeah, the bactoprenol, I do not care for you to know either. Rather, knowing that bacitracin inhibits cell wall synthesis, or inhibits, really what it's inhibiting is the ability of bactoprenol to pump out those NAG and NAM precursors. That's really what's happening there. So those are the three proteins I do not care for you to know.
So you don't need to know the bacitracin?
You need, for bacitracin, you need to know what it does, but you do not need to know the protein. Okay? Abby?
Do we need to know specific examples of every class?
No, that's more, honestly, that's more for your guys' benefit, because there will be times for many of you in here, as you are planning on going into nursing, you will come into contact with these antibiotics. And for me, I don't know why. Maybe it's just the fear that I know someday I will probably have to come to you for help. And I will quiz you at that time on whether ampicillin is a beta-lactam or not. Okay? And if you get it wrong, I will leave the hospital no matter how deathly ill I am. But these are terms that you're going to see come up. It's more just as a way for you to start connecting the relationships. With those specific examples, no. What I have done on past exams, and you'll see this, is that I might say something like, carbapenem is a beta-lactam. I've defined the antibiotic, but that's not where the focus should be. The focus should be on what class it's on. Okay? So that's what, I mean, those specific examples are just kind of classical ones that I wanted you to be aware of more than anything else. Caleb?
What was the first one? What was the other one?
It's the one under isoniazid and ethambutol. So there's a protein known as INHA, and I can't remember the other one that's on there. But the one that does not have a true protein target that you guys should be aware of, and I've noted this, polymyxin B. Polymyxin B inhibits, actually destabilizes the outer membrane, and so that one doesn't have a true protein target. It does have a specific target, though, being the outer membrane. Any other questions on that list?
Is all this information we decided on the key?
It is on the key. the information in terms of like what I'm not asking. Mostly it was 4 to 6 or 5 to 7. So, beyond my better judgment and need for sleep, I will be here from 4 to 7. And what I will do is what we cover in the first hour, I will cover again from 6 to 7, because I know some people have class at 4 to 5, and some people have class from 6 to 7. So I didn't want to like repeat that information in back-to-back hours. So if you come at 4, by 6 o'clock you'll have heard, I hope, everything that I'm anticipating on covering. If you come at 5, by 7 you'll have heard all the information as well. Okay? Drop in as you want, leave when you want, bring some dinner with you, bring a sleeping bag, etc. Any other questions? All right. I will be in my office today from 2:30 to 4. I'll be around as well from roughly, I said that I would be around from like 9 to 11 this morning, or 9 to 12 this morning. It's going to be more like 10 to 12. I have a couple of things that have come up. And then Friday I'll be around in the afternoon as well. So those are additional times you can come by and meet with me if you'd like to. All right. And then I'll make a couple of more announcements in lab tomorrow about some things that are coming up, because I realize that the next like 5 days, there's a whole lot of stuff going on. So I'm going to try to debulk that a tad to help out. All right. Well, 17 of you or 18 of you already answered. So let's go back to this question. This is actually one that we finished off with on Monday. And the question was, why is polymyxin B only used topically? And we started hitting on the idea of therapeutic index. And if you remember, what we said was, what is the therapeutic index, mathematically speaking? Yeah, so it's basically the toxic dose divided by, oops, I guess those are both T's, therapeutic dose is equal to the therapeutic index, or chemotherapeutic index. Basically, this is a measurement of how much, in some ways, does the amount of drug that you will need to clear an infection, is that also going to cause somebody to be ill? We want this therapeutic index to be quite low. We want one in which the amount that it takes, we want it to be large. I apologize. I always screw this up. We want the toxicity of the drug to be very low, therefore the toxic dose to be high. Somebody has to take a lot of it to get ill. We also want the therapeutic dose to be really low. We want it to be effective in killing the microorganism. And so the larger these therapeutic indices are, the better. Emily. Yeah, I can. So again, the concept here, one of the things we covered at the end on Monday was that a high toxic dose means that the drug has low toxicity. Okay? So a high toxic dose means you have to take a lot of it to become ill or to experience side effects. We want our therapeutic indices to be large. We want them to have, the drugs to have a high therapeutic dose, but we want also us not to have to take a lot to kill the microorganism. And so we want that therapeutic dose, the amount that it takes to clear an infection, to be really low. In other words, we want to take drugs at concentrations that are well below the toxic dose, so that it doesn't cause side effects. Okay.
So we want the toxic dose too high,
Yep, resulting as that ratio, exactly. Now this therapeutic index and toxic dose can depend on a number of different factors. So for example, toxic dose is oftentimes reported in an amount per kilogram. But we also need to keep in mind that it's not only weight that controls an individual's, the toxicity of a drug. So, for example, Somebody who is elderly might be more affected by these drugs than somebody who is a young, healthy adult. And so the toxicity, the toxic dose for an elderly patient might actually be lower than it is for a 20-something. So there are other factors that can contribute to that, whether the individual is immunocompromised, for example. So in this case here, polymyxin is only used topically. It doesn't have to do with the fact that it targets the outer membrane or that it's gram-negative per se. It doesn't have to do with the fact that it's a high toxic, it has a high therapeutic index. That'd actually be really, really good. It's actually that polymyxin B has a pretty low toxic dose. And we can't handle it internally. It actually makes us sick. I'm pretty sure that might be why if you look at a tube of Neosporin or triple antibiotics ointment, it says, if ingested, call a doctor right away. Okay, it's toxic. It's not good for you. And so another way to think about toxic dose is this term selective toxicity. And what we mean by this is that most of the microbial targets for antibiotics are unique to bacteria. Do we have peptidoglycan cell walls? Our cells don't have that. Bacterial cells do, though. And that's why penicillin is such a great antibiotic, or those beta-lactams are such great antibiotics. They target something that is selective or unique to bacteria and don't target something that we find in our own cells. Polymyxin B targets membranes. Do we have membranes on our cells? Heck yes. Okay? And that makes it not as selectively toxic. Now, there's a caveat to this as well. So for example, chloramphenicol. What's the target of the chloramphenicals or the aminoglycosides? Ribosomes. Do our cells have ribosomes? But these drugs are still selectively toxic for bacteria because our ribosomes actually have a slightly different structure than bacterial ribosomes. And that's what allows for these antibiotics to work against bacterial cells and not our own cells. Okay? Same thing with the gyrase inhibitors, the quinolones. Same thing with the RNA polymerase inhibitors, rifampin. There's enough difference between our versions of those proteins and bacterial versions of those proteins that allow for that selective toxicity to occur. So I'm going to pause here because this is a pretty important point and just see, are there any questions on that concept? Devin.
Is that like the membrane too, how you said that, like we both have membranes, that the membrane is like, has different things in it that will allow the antibiotic to not target our cells?
In large part, though, a phospholipid bilayer is a phospholipid bilayer. There really isn't much difference. The only thing with gram-negatives that's different is that LPS. That doesn't really seem to have an effect, though, on the ability of polymyxin to cause an effect. Yeah. Erica.
So does the peptidoglycan have no effect?
Say that again?
Does the peptidoglycan, that has no effect really? So we don't have it, but the bacteria cells do.
Mm-hmm.
But then the ones that are targeting the membrane, that doesn't.
Right, so the idea here would be if you're treating somebody with penicillin to treat a staph infection, for example, it doesn't happen anymore because staph is resistant to it, but nonetheless, let's go back to the 1940s. Okay, treating with penicillin would have inhibited the growth of Staph aureus because what penicillin does is it binds to penicillin binding proteins, and we'll go through this mechanism a little bit today or on Friday, depends on our speed. Binds to penicillin binding proteins, which are unique to bacteria, and inhibits the synthesis of their cell wall. We don't have those proteins. Penicillin is a competitive inhibitor of those proteins, and since we don't have them, it has no effect whatsoever on us. Okay? It's an inert compound when it comes to a human cell. However, like with polymyxin, since it has the ability, it really just makes the membranes more leaky So it increases the permeability. Since we have phospholipids, since bacterial cells have phospholipids, it'll have the same effect on both of our cells. And so that's why when we're looking, this is one of the biggest reasons why drugs go through phase trials in some ways. Because we're establishing what is the toxic dose, but we're also establishing sometimes, even before we get to phase trials, are these drugs selectively toxic? So antibiotics, before they even hit the phase trials, will be tested against bacterial populations, and then will be tested against human cells to determine, does it kill either of those populations? And you want ones that will kill the bacteria but have no effect on the growth or the survival of human cells. That's ultimately what we want. Any other questions? Kaylin.
What does the T on the top stand for?
Yeah, that's toxic dose. Toxic dose, sorry. All right. Let's go to the next one. Which of the following is a narrow-spectrum antibiotic that inhibits the synthesis of mycolic acid? Excuse me. Drinking problem. So this is a fairly straightforward one, and as the answers come in, let me ask the follow-up question. Where do we find mycolic acid? On what type of bacteria do we find mycolic acid? Acid fast, good. And that the typical example of those acid fast, Mycobacterium. Again, that's where they get the name Mycobacterium. Anybody remember the properties of mycolic acid? Yeah, it's likely that our cells, particularly macrophages, can overcome the inhibition of phagocytosis that's imposed by the mycolic acid. And so it's kind of a two-hit effect here. And oftentimes, well, which one is it? Anybody know the answer to this one? Yeah, it's the isoniazid. Oftentimes, isoniazid is also prescribed along with rifampin to treat mycobacterial infections, Mycobacterium tuberculosis in particular. However, we're finding drug-resistant strains. It's kind of evolution in action. All right, next one. What's true of all beta-lactam antibiotics? They are narrow spectrum, they inhibit cell membrane synthesis, they have a common ring structure, or they are non-competitive inhibitors. Now, this may not be in that table, and so this is one that we'll kind of ad-lib on a little bit afterward. Should we take a look? All right, not too bad. So definitely not narrow spectrum. Some are narrow spectrum, and if they're narrow spectrum, they're targeting gram positive. Some are able to get through that outer membrane of gram negatives, and they've been modified in ways to allow them to. The beta-lactams are kind of a large catch-all class that include penicillins and its derivatives, the cephalosporins and its derivatives, and then also what we call monobactams and the carbapenems. Bacteria have found ways to gain resistance to every single one of these drugs. Yay! Ask why I'm such a pessimist, and then you just study antibiotics and you'll understand. These are competitive inhibitors. They bind to proteins known as the penicillin binding proteins. Specifically, what they do is they will bind and inhibit. I'm going to pull up some slides for this one. Specifically, what they end up doing is they end up competing for the binding to the penicillin binding proteins with the substrate. And the substrate for these penicillin binding proteins, if we go back to cell wall synthesis for a few minutes, or a few seconds, you might remember one of the features of this synthesis is NAG and NAM. And then we've got these peptides that help to hold those individual NAG and NAM strands together. This is what penicillin binding proteins do. They attach these they attach those peptides together to provide that longitudinal strength that we've talked about. Now, what the penicillin and its derivatives do, they compete for the binding in this active site, and in doing so, basically just inhibit the function of the enzyme. They prevent the enzyme from being able to bind to these peptide bonds. It looks something like this, so you can already see that there's a similarity in the structure there. Okay? And all of them, where's that ring structure that we're talking about? What ring structure, when we refer to the beta-lactams, is present in all of them? It's even in color. The one in red. That's known as a beta-lactam ring. Every single one of these, the monobactams, the carbapenems, the cephalosporins, the penicillins, all have that classical structure. It mimics the D-alanine, so those two amino acids that get formed in this cross-peptide bridge here. Yeah, I think that's all we need to talk about with that one. All right. Questions on the beta-lactams? We're going to come back to them a little bit later because we'll talk about how bacteria inhibit their functionality as well. The bacteria on a particular type of agar, that agar has to be poured to a particular thickness, 4 millimeters, because the thickness of it can actually affect how fast the antibiotics diffuse from that central ring. And really in this case, what makes this Kirby-Bauer assay different than what we talked about with the chemical control is that because it's so highly standardized, we're actually able to determine at the end of the day, is an individual strain sensitive or is it resistant to that antibiotic compared to other strains of the same species? So for example, let's say that you are working with a patient, you isolate a strain from that patient that is Pseudomonas aeruginosa. You can perform a Kirby-Bauer assay to determine, is this particular strain, relative to all the other strains that we know about Pseudomonas, is it considered to be sensitive or resistant to this antibiotic? And that then can help you to determine which antibiotic will you use to treat the infection. Okay? And that's what that table then below this figure represents. Is it represents those standardized zones of inhibition in millimeters to determine is the organism, this particular strain, sensitive or resistant. Now we don't have the same sort of standardization for some of the chemical methods of control that we talked about, like bleach or alcohol, ethanol. And so in those cases, the best that we can do is to say, for this particular strain, which of these chemicals works the best, and then we can also say between strains, on which is the chemical more effective. That's what we can say. So, by definition, what is the zone of inhibition? Or how do we measure it? Ashley? Exactly. So given a normal plate size, I would measure from here to here for this one's zone of inhibition. Okay? We'll talk about an exception of this in a second. So for On this particular figure then, for ampicillin, what did folks get for the zone of inhibition? What was that, Abby? 25? Anybody get 26, 24? In that range is good. 25 plus or minus a millimeter or so. Okay? Kaylin?
Does it matter if you go like this or like this?
No, it shouldn't. It really shouldn't. If you have oblong ones for some reason, I would say that what you might want to do is do both and then average them. But yeah, but that really shouldn't happen. It should relatively be very circular around, because what we're assuming is from that disc, you've got equal diffusion of that antibiotic from that disc into the media. And as it's diffusing out, here's the highest concentration. As it's diffusing out, that concentration is decreasing. So really where this zone begins, this is in some ways what the concentration of the antibiotic is right there. What is that concentration? It's our minimal inhibitory concentration. It's the minimal concentration of antibiotic that's needed to inhibit the growth of bacteria. And we can't define that in this particular, we can't define that concentration in this particular assay. And that's why ones like the E-test and that broth dilution assay have been created. So how about in the case of something like chloramphenicol on this disc here? How do we measure that one?
Measure the radius times by 2.
Multiply by 2. So Dana, what did you get?
So I got 80 millimeters.
Okay. Anybody somewhere around there? 70, I think when I measured it was like 76 I had or something like that. It might depend on where you're measuring from or where you're measuring to, but that works. What about penicillin? Yeah. If the cells or the bacterial strain grows all the way up to the disc, we call that 0. So you will never find in a Kirby-Bauer assay a measurement of 1 or 2 or 3 or 4, maybe even 5 millimeters. Usually the smallest diameter that you can measure is 6 millimeters, typically. That's always going to depend on the size of the disc, but that's just typical. Meg?
Did you say that the outer ring, like the farthest right back of the zone? Or is
Yes.
that the minimal inhibitory?
So the minimal inhibitory concentration would really be like this interface between those two
Okay.
locations. Absolutely. Okay. Given what we just said then, I'm not going to go over the last one. It's trimethoprim and sulfamethoxazole, which are two drugs that are often combined together as a sulfa drug. Given the zones of inhibition that you've measured, next determine, is this particular strain relative to other, this would be relative to other Enterobacteriaceae, which include the E. coli, Enterobacter, etc. Is this one considered to be sensitive or resistant to those various antibiotics? I'll give you a minute to look through and just write down for yourself. Sensitive, resistant, intermediate. Okay. We're just kind of going through some of the homework from last night and how to measure these zones. What's that? Then it's considered intermediate. It's not really considered sensitive or resistant. Yeah. All right, so.
There's just a question.
Oh, okay. Here.
So, thank you. So are these little circles at the beginning, or is it like just, do they grow?
They grow. We'll talk
that's
about
what I
that.
figured.
Yeah, we'll talk about that. All right, so for these particular ones, is the organism sensitive or resistant to chloramphenicol? Sensitive. The zone of inhibition, that 80 millimeters that we said, is greater than what's required for us to consider it sensitive, which is 18 millimeters. Okay? That's how you read these. Ampicillin, sensitive. The sulfa drugs, Intermediate, so that would be one that you might say like, yeah, it's not the best antibiotic to use. If it's our only option, maybe we can use it. Penicillin. Resistant. Why? Why is it resistant? Something I didn't mention about this, but that's in the header of this. This is a gram-negative. What does penicillin specifically work against? Yeah, it's a narrow spectrum. And again, I'm not asking you to know that, but if I might define it as being a narrow spectrum drug and say it doesn't work against gram-negatives, what you might be able to predict or to assume is that it only works against gram-positives, that there's something about gram-negatives inhibiting its ability to function. The E-test, I wanted to point out real quick, is really nice because it's got a gradation of concentrations. And actually using an E-test, you can identify the minimal inhibitory concentration. It is the point at which the bacteria grow all the way up to this strip. So in this case here, this is tobramycin is the antibiotic. 0.064 micrograms per mil is the minimal inhibitory concentration for tobramycin to inhibit the growth of the bacteria that is on this particular plate. That's how we read those. I'm just going to skip ahead to this last slide real quick. We will come back to this on Friday. So bring these sheets with you. We will continue to work on them, but feel free to go ahead with them if you want. Broth dilution assays are typically done starting with a certain concentration of antibiotic and then performing 1 to 2 dilutions. So whereas in lab yesterday we were performing 1 to 10, you would do 1 to 2 dilutions where you're mixing, for example, 100 microliters of the previous concentration with 100 microliters of straight LB. Typically then what we find is if we were to label these, this would be like 16, 8, 4, 2, and 1 microgram per mil of these various antibiotics. And we look at the first concentration where no growth occurs. That's what we define as the minimal inhibitory concentration. Okay. So for the case of kanamycin, again, if this was 16, 8, 4, 2, and 1 micrograms per mil of antibiotic, what is the minimal inhibitory concentration? 4. What about for something like streptomycin? At least 1, not any larger than that. We'd have to go further to determine. What about something like sulfamethoxazole, where there's even a tiny pinprick of growth right here and here? And this is where sometimes reading into a methods section of a paper can be helpful. From this particular paper, what they defined was that the MIC is the concentration that inhibits 90% of the growth of the microorganism. So using that definition in this case, you might say it's 4 micrograms per mil of the sulfa drug. Okay? So, to recap what we talked about today, the major take-home points. 1, knowing the particular antibiotics, knowing the targets, knowing the processes that they inhibit. And again, the reason for this is 1, so that we can make decisions on what drug to provide in which condition. Not all drugs work against all microorganisms. Some are much more toxic than others. Some of the really new ones that we've come up with are really bad for us in some ways. And I don't mean it from a holistic peace to the world, bad for us sort of way, hippy-dippy way, but they make you physically ill because the toxic dose is pretty low relative to the therapeutic dose. The other thing that I want to point out with some of those drugs, I don't remember the other thing I was going to say. So decision making and thinking about, do you prescribe a broad or narrow spectrum? And we'll spend more time talking about that later. The other thing is, how do we measure effectiveness here? So we've talked about, we've gone over one of these methodologies. You can bet that on the exam there is going to be a question related to zones of inhibition. On Friday I will go over the topics that are on the exam so everybody's aware. Broth dilution is what we'll finish up with. my plans for Friday were to watch a TED Talk and to have you guys do a homework assignment on that TED Talk. My fear is that I'm going to be trying to cram too much stuff into that small amount of time. But this is to me, it is one of the best TED Talks on antibiotic resistance. And so I want to make sure that we do it. We won't do it Friday, but we will push it back to later on in the semester. It's one that I feel like we have to come back to. It's incredibly important to me. So, no homework for Friday. All right? Take the time to study. Take the time to review this material, because we will spend more time talking about the antibiotics on Friday. And we need to still talk about methods of how microorganisms overcome these antibiotics. And that's where we'll finish up on Friday. Claire?
Well, I just have an
Okay, that's it. Have a good afternoon, a great morning and afternoon.
So this is log 10 and that equals